Welcome back to our course on probability theory. We were starting to introduce conditional expectation, and today we're continuing. And as you heard in the last video, conditional expectation is the expectation of a random variable given a sigma algebra. The sigma algebra is a subset of the full sigma algebra, and today we are covering the case where the sigma algebra we are conditioning on is generated from a second random variable. This might sound special, but it leads to some very intuitive meaning of the conditional expectation. So let's see. So let's get started. With this case, g equals sigma of x as it's written here, which means that the sigma algebra we're conditioning on is generated by some random variable. So let's recall from last time. The conditional expectation of y given x, or that's something we will have today. What we had last time is we had the conditional expectation of a random variable given a sigma algebra. And here, as you already see, we will define the conditional expectation of one with respect to the other random variable, as is written here. Random variable is exchanged by its sigma algebra. And the definition, we always had the defining property of the conditional expectation. We had that this object, the conditional expectation, is the almost surely unique random variable such that for all x measurable sets which are written here, so that's clearly x measurable, the conditional expectation can be exchanged by the random variable we are conditioning, we are computing the expectation of, like this here. So this here holds, and this random variable is x, or sigma of x measurable, then this is the conditional expectation. So when is some random variable, as written down here, the conditional expectation, measurable with respect to the sigma algebra generated by x? We had that already in some earlier proposition, I think, maybe also recalled here. That's the case if and only if we can write down the random variable as a function phi of x. So if this here holds, phi of x satisfies the defining property of the conditional expectation, and we have phi of x equals the conditional expectation, almost surely. Yeah, and we can combine this now, or yeah, as we have it here. X is a random variable and z is a real valued random variable, and we want to see when is z sigma of x measurable. That's the case if and only if we can write z as phi composed with x. Let's make an example, and we had this already, the random success probability. So I claim the probability that x equals k, so I have k successes, given that the random success probability is u, is given by this here. Well, that's somehow pretty intuitive, because conditionally we know what u is. Yeah, well, we would write down the binomial distribution here as it's written down here, because x has the binomial distribution with n and the random u here, but we're conditioning on this here. So let's see if that holds true. And we're doing this by computing this conditional expectation. So we're computing this here on the left-hand side. So what is this? That's the probability that x equals k and u is in some set I. How would you compute this? First, you have to see what the u is. K choose, that's the probability du, it's in I. And then there's a chance of k choose n, u to the power of k, 1 minus u to the power n minus k, that I have k successes, as it's written here. And I can write it differently. I can write it as k choose n. That's a big U now to the power of k. 1 is big U to the power n minus k. Integrated over the set u in I. And now we see here, this here is a u measurable random variable because it only depends on u and satisfies the defining equation for the conditional expectation. So this here is the conditional expectation as given here. Okay, next example. That's also nice here. So we have independent random variables which are IID, identically distributed and independent with some expectation, and Sn is their sum. And I can compute two things. I can compute the expectation of Sn given x1, or I can compute the expectation of x1 given Sn. So what would you say if you know x1, what's the conditional expectation of Sn given x1? Okay, they're independent. And for independent, we had something last time. That wasn't this big thing here. If x is independent of the sigma algebra, then I can forget about the condition. That means here, if, for example, x2 is independent of x1, then the conditional expectation of x2 given x1 equals the expectation of x2, which is mu. So let me write down Sn. Sn is x1 given x1 plus expectation of x2 given x1 and so on, plus expectation of xn given x1. Well, what is the conditional expectation of x1 given x1? Well, x1 is actually x1 measurable, and there's only one conditional expectation of x1 given x1, which is x1 itself. So this here is x1 plus, and here we have that x2 is independent of x1, so I have here a mu, and I get n minus 1 things, mu, like this. Okay, the second one is a bit trickier. Here, condition on the sum, and I want to compute the expected value of x1. However, there's a trick. By symmetry, I can exchange x1 by x2 and by x3 and so on. And therefore I can also write that's the conditional expectation of xk, conditional on Sn, k from 1 to n by symmetry. So what can I do? I can pull the sum in here and have Sn given Sn, which is Sn. So it's 1 over n times Sn. And when you think about it, that's also quite intuitive, because I tell you the value of the sum and I ask you, what do you expect? What's x1? What is one of these things here? So, well, I don't know better, 1 over n times Sn. So they're all the same size, such that they sum up to Sn. Next example, which is a famous one, Buffon's needle problem. I mean, there are various variants for this. These vertical lines have a distance of 1. And the needles themselves, they have length 1. And the question is, what's the probability when you throw such a needle on the plane here? What's the probability that it intersects with a vertical line? Okay, what's the probability of intersection? So here it doesn't, here it does. How can you compute this? And that works as follows. Yeah, the position or how it that's located on the plane is determined by an angle, theta here, and the distance to the next vertical line. The distance to the next vertical line is something between 0 and a half. And the thing is, given theta, given the random angle here, the probability that I have an intersection here is actually simple. Because that's the probability that x, the distance, is, well, smaller or equal to 1/2 sinus of theta. So that's this thing here. Or x is down here, x is bigger or equal to 1 minus 1/2 sinus theta. Of course, given theta. X is, of course, uniformly distributed between 0 and 1. So this probability, given theta, so I can use the right-hand side here, is, well, this value here, 1/2 sinus theta, plus the area between 1 minus 1/2 sinus theta and 1, which is again 1/2 sinus theta. So in total I have sinus theta. And then I can use the so-called tower property as we had it. The probability that z equals 1. So the tower property last time it was, if I have h subset of g, then the conditional expectation of the conditional expectation of some random variable x given g, and this here given h, is the same as the conditional expectation of x given h. And in this case we have that h is trivial, so only the empty set and the whole set is in there. And that means here I have the expectation of x, and here I have the expectation of the conditional expectation. This here is the conditional expectation, and this here is the expectation of the conditional expectation. So probability that z equals 1 equals the expectation of the conditional probability. The conditional probability is sinus theta. And what's the probability, what's the expectation of sinus theta? So theta is apparently uniformly distributed between 0 and pi over 2. So 2 over pi is the constant I need in front of it. I'm integrating here sinus theta between 0 and a half. So this integrates to 1 actually. And the probability is 2 over pi. Okay, that was a nice result. And we have one last example for today. Yeah, which is maybe not that nice, but very practical. So what's the problem here? I'm searching something in a list. I'm given n names of persons from R cities. What else here? Each person comes from city J with probability Pj. I'm storing these n names in R unordered lists. And then a random person comes to me and I want to look for him or her in the lists. If the person is not ready recorded, you need some comparisons to make. So you need to compare the name of the person that stands in front of you to the person which stands in the list. J is the number of the city from which the person to be searched from comes. So that's a random of these J's here. Zj is the number of people from city J in the list. And the number of comparisons I need is L, which is Z equals J. So Z equals J, Z index J, with a random J, which is the J that, that's written down here. And how can I compute the expectation of L? Again, I need the tower property, and I'm conditioning on J. Condition expectation of Zj equals J. Well, I know J now here. I know the city where the person comes from. Zj is the number of people from city J in the list. There are n in the list, and every one of them has a probability of Pj to come from city J. So this here is n times P capital J. So I have to compute n times the expected value of P capital J. And J, big J, equals small j with probability Pj. And the value I have to validate is Pj again, n times sum over all j. So I have this here as the expected number of unsuccessful comparisons. And as you see, this tower property here plays here a role, and also played here a role, and that's often very convenient in calculations. Okay, great. Next time we are dealing with something else, which is conditional independence. See you then.